Hello everyone and welcome. Let's get right to it. Given a 6x6 southern pine fir south number 2 supports an upper floor, as you can see right here. The post has a height of 9 feet. The ends are held in position. However, no other bracing occurs along the length of this post. The post is subject to normal conditions. What I mean by normal, its temperature is normal and the moisture content of this post is also normal. Nothing crazy going on here. What do we want? We want to determine the allowable capacity of the post. What we'll be using the NDS, the National Design Specification for Wood Construction, the 2015 edition. We will also be using the NDS Supplement, the National Design Again Specification, but this is the design values for wood construction, and we'll be using the manual. If you go to the manual, if you go to table M4.3-1, you'll find this table, and this is the adjustment factors for saw lumber. Now we could skip all this stuff. We'll be focusing for the compression parallel to grain and the yaw modulus for post or columns, E-min. And I have it highlighted here, so as you can see. Now you pull those factors. This is what we have for the factors. You have FC times CP. Now FC is little star is just this right here. FC we're gonna find that in the NDS supplement. The duration factor here is going to be 1. We're assuming it's just live and dead. The size factor, if you could see here, you'll find that in your supplement. In your supplement, if you go to 4.3.6, if you read this, I'm not gonna say it, but it's just saying that if the depth exceeds 12 inches, then you have to use this equation. In our case, it's a 6x6 post, so we're going to say, or now we're going to say, but it is CF is 1. CP is the column stability factor, and that we have to definitely use. We have to figure out what that is. So duration is 1, size factor is 1, CP we don't know. So in the end, we have this equation over here. FC prime equals to FC times CP. And then the yaw modulus for columns, post, E-min, it just remains the same, doesn't change. Now, in your NDS supplement, table 4D, it gives you the reference design values for visually graded timbers 5x5 and larger. And we are using spruce pine fir south number 2. So if you go where it says FC compression parallel to grain, we have the FC equals to 425 psi. And then modulus of elasticity, E-min, is 370,000 psi. Now that we have that, we could solve for the column stability, CP. For the column stability, you go to the manual. This is from the manual, NDS manual. And this, I'm just going to quickly read. It says, when a compression member is supported throughout the length to prevent lateral displacement in all directions, CP equals to 1. However, we don't have that condition. It's unbraced. So we have to find what CP is. Here, 3.7.1.2 just talks about how to get KE. You could get it, just using engineering mechanics. And I'm just going to let you know that it's pin support, so KE is going to be 1. L is just the length of the unbraced support. So the post is 9 feet and is unbraced throughout the 9 feet. So L is going to be 9 feet. In our case, we want it to be in inches, so we want that to be 9 times 12. We convert it from feet to inches, so it's going to be 108 inches. Now, 3.7.1.3, it talks about the effective length ratio. The effective length ratio is going to be L, the length, divided by D. In our case, because we have a square post, it's just L over D. If we have a rectangular post, you have to use the smaller of whichever, either LE1 over D1 or LE2 over D2. Now you could see this in figure 3F in your manual. Again, our KE is going to be 1, so that's good. Our effective length ratio, LE over D, cannot exceed 50. All right, so what do we have here? Our effective length ratio, LE over DE, is just the 9 feet. We convert that into inches, so we have 108 divided by the width or depth. In this case, is a square, so it's 5.5 inches. When you divide that, you get 19.63, which is less than 50, which is good. Okay. Our compression parallel to grain, which we got earlier from our supplement, the NDS supplement, is 425 psi for southern pine fir number 2. Now I know I'm going pretty quick, so I'm gonna slow down a little bit. First, always you wanna get the effective length, perfect, and you wanna get the compression parallel to grain. We got that too. Now that we have that, we have to use the column stability factor, which is this huge equation. I know it looks confusing, I know it looks long, but it's not so bad. You kind of have to break it down so it could make some sense. Now, we have FC. Now, there is a factor here, FCE, which is this right here. FCE equals to 0.822 times the yaw modulus for buckling for columns, E min, divided by the effective length ratio to the second power. C here is 0.8 for saw lumber, which is we have. If you have something else, if you have something round timber, or you have in like structural glue laminated timber, you're gonna use different CE. In this case, our CE is 0.8. So we have to find out what FCE is, and I have it right here. FCE is 0.822 times the yaw modulus for posts for columns, which is 270 psi. You're gonna divide that by the effective length ratio to the second power, which we get 789.29 psi. Now, like I said, we have to break this down because it's just long. It's just a long equation, and I don't want you guys to get lost. I don't want to get myself lost either. So we got FCE, and this is FC prime or FC star. FCE is 789.28 and FC is 425. So just divide that because we're going to be using that a lot. So you're going to use it over here, you're going to use it over here and over here too. So might as well just get that. So when you divide the FCE over FC, you get 1.85. 789.3 divided by 425, you get 1.85. So we have everything. We have this ratio, we have C. We go plug everything into this equation, and we're going to solve for CP. So 1 plus FCE over FC is 1.85 divided by 2 times 0.8, which is, this is C right here, minus the square root of 1 plus 1.85 divided by 2 times C, which is 0.8 to the second power, minus again FCE over FC, 1.85 divided by C, which is 0.8. You plug and chug, just plug and chug. You're gonna get 1.78 minus 0.82, and in the end you're gonna get CP. CP is 0.86. So you're losing strength in a way. Is accounting for the slenderness and how it's going to buckle the post. And think about it this way. Let's say you have a ruler. You have a ruler, and try to compress it. Put your 2 hands and try to compress it. And it's gonna buckle. You're gonna see it's gonna bend about the weak axis. It doesn't bend about the strong axis. It's gonna bend about the weak axis. Now let's say you have the same ruler and you cut it in half because it's smaller in length. It's gonna be stiffer, so it won't buckle as easily compared to if the ruler was normal, 12 inches. Now let's say you have the ruler, and let's say, just imagine that the ruler is thicker in width. It's pretty because it's very thin about one axis. So let's say that axis that's very thin, it becomes thicker. Then you apply the same load and you're gonna see that it's not gonna buckle as easily. So this equation just takes care of that. So in the end, we have 0.86 for our CP. Now that we have that, we have everything. We go solve for FC. FC is FC prime is FC times CP. So FC prime equals to 425 psi, which we got earlier, times 0.86. And in the end, we have 365.5 psi. Now to get our allowable capacity is just the FC prime times the area of the lumber of the post. It's a 6x6 post, but in actuality, when you go to Home Depot, it's a 5x5, 5x5 inches. So we have the stress, 365.5 psi times the area, 5.5 times 5.5. We have an allowable load of approximately 11,000 pounds. So that's pretty much it. This is how you find the allowable capacity for a 6x6 post. Thank you and have a great day. Bye bye.